Hey everybody, my name is Kelvin and welcome back to episode 10 of my Learn Python series. Today, we're going to be taking a look at object-oriented programming. This is one of the most important parts of Python because pretty much all of Python is built around objects. If you've paid attention in the last 9 lectures, we've already been using objects in pretty much every single episode. Strings are objects, lists are objects. When you write something like name.lower, or items.append, we're going to be calling a method on an object. The goal of this video is to go over object-oriented programming principles from the ground up. By the end, you should be able to answer a couple questions like, what is a class? What is an instance? What is a method? Object-oriented programming, or OOP, is essential for software engineering. A lot of technical interviews will really test your object-oriented programming skills. Take that from me, as someone who's sat in on many of those interviews before. As always, the course repository is linked in the description, and of course, I recommend watching the earlier episodes before this for the best learning experience. Before we dive in, I have something I'd love to share. Have you ever wondered how the biggest companies in the world organize, sort, and analyze their data? It's from the work of data engineers. Data engineering is the backbone of modern analytics, business intelligence, and machine learning. Data engineers in the US earn around an average of $130,000 per year, with some even making over $200,000 annually. Hi, my name is Kelvin Lin, and I wrote this book because this is something that I wish I had when I first started out. From databases, data warehouses, and real-time data streams, this book will give you a great foundation to launchpad your data engineering career. This is Modern Data, from Ingestion to Production. Available on Amazon, Apple Books, and Barnes & Nobles, so get your copy today. Welcome back. Let's jump straight into Lesson 10. We'll start by creating a Lesson 10 folder like usual. Here, we'll first initialize our exercise file. We'll start with 10-1.py following a regular naming scheme. In this section, I want to help you understand what an object is without introducing the concept of classes just yet. An object is simply a value in memory. It contains data, and it has behavior. The behavior is exposed through things called methods. A method is essentially a function that belongs to a specific object. A rule of thumb is when you see a dot or a period, you should think, I'm accessing something that belongs to an object. That something could be a method, or it could be a data. Data stored on an object is simply called an attribute. We're going to review strings and lists because you already know them. We'll call methods on them and observe what happens. We'll start with a string. Text is equal to hello world. We'll print this. Strip is a method on a string. It'll return a new string with white space removed from start and end. Here, we know we're calling a method because of the period right here. We can also do a lower method, which we can call with the lower method, like that, and we can print that. Print cleaned, and we'll print lowered. When you run this, notice that the original text did not change. And then we'll also print text. And we'll run this. The thing to notice here is that the original text did not change. We can see that it's printed up here. We'll see that it was printed first using the print function and printed down here after the transformations. But the thing is, if you notice right here, the text string has not changed. That's because strings are immutable. Methods like strip and lower will return new strings instead of modifying the original. Specifically, the string methods like strip and lower are designed to return new strings instead of modifying the original. Let's take a look at a list. I have a list of names with my name, And we'll have a John in here. We can print the names. And now here, we'll call the append method. And we'll append a name, Noah. And then we can print this. We can do this because lists, again, are mutable. We can run this. And we'll see that our original list has been modified. And we'll see that our original list has been modified. That's because lists are mutable. They have different behavior than strings. It's still the same idea, though. We have an object, and you are calling a method that belongs to that object. Let's dive into the next exercise. We'll create a file called 10-2.py. And here, I want to cover your first class and your first instances. What is a class? A class is simply a blueprint. It defines what kind of objects you can create and what they can contain. An object created from a class is called an instance. The words object and instance are often used interchangeably, but it helps to be precise. The class is the definition. The instance is the actual object you create. We'll start with the smallest possible class. In Python, an empty class uses pass. Pass basically means to do nothing. It's a placeholder, so the class block is valid, and the code will work. We define a class using the class keyword here, and we'll call our class here person, and then we'll simply just pass this. This defines a class named person. This does not create a person object just yet. It only creates the blueprint. To create an instance of class, you have to call the class like a function. So if we had a variable called p1, we can set it to a new instance of person, like so. And we can have a p2 is equal to another instance of person object. And then we can print this, p1, print p2, and print type of p1. And when you run this, we should expect to see that p1 and p2 are separate objects. And the type of p1 will show that p1 is of type person, because it is an instance of the class person. We run this, and we can see a person object at these memory addresses, and our type of p1 is a person. Let's give these objects data now. Data stored on an object, if you recall, is called an attribute. We can assign attributes using dot notation. Get rid of these. Dot notation is our period right here. We can do p1.name is equal to Calvin, and we can do p1, my age is, say, 30. Not at my actual age, but it's just an example. And we can set attributes on p2 as well. And we can have John, and let's say John is 60. Oops. We'll keep these as integers, actually. Notice that these attributes can be of any type. And let's print these. Again, we'll use dot notation. Again, we'll use dot notation to access the attributes. And we see that we've successfully printed what we expect to see. This works, but it has a real problem. Python will not stop you from forgetting an attribute. You could create a person and never set any kind of age. Then later when you try to read p.age and your program crashes with an attribute error. That's why classes almost always define something called an initializer method. The initializer method will give you consistent creation process. The special method here is defined like this. 2 underscores, init, and another followed by another couple underscores. And init here is a special method that will run automatically when you create a new instance. It's a method that Python knows to call for you. Say we wanted to create a person object with a name and an age, like down here. We'd have to do something like this. Pass in self. The first parameter of every instance method is self. Self is the current object. It's basically how you refer to this person inside the class. We can rewrite person so that the name and the age are required when you create an object. So we'd have to do something like this, self, comma, name, comma, age. Oops, we need a def right here. And we'll set self.name is equal to the name parameter that we pass in here. And self.age is equal to the age parameter that we pass in. And now here, we've successfully set the attribute of this person object to whatever you pass in for name. In this case, Kelvin and 30. So now that we have our constructor, every person is now guaranteed to have a name and age because init runs every time a person is created. The point of that is to make your object predictable. Let's add a print statement here and let's demonstrate that. And we're going to create a person object with John, and he's 60. And now when we run this, we'll get exactly the same thing. But now here we can see that we created 2 separate person objects and we set the attributes name to Kelvin 30 and John 60 within each separate person object. Let's jump into exercise 3. In this exercise, I want to cover that methods will define behavior. In this exercise, I want to cover methods. Methods, as we've established, define behavior for your objects. A method is a function that's defined within a class. The reason methods matter is that behavior should live with the data it belongs to. If you have a person object like before, it makes sense for the person object to know how it introduces itself. It also makes sense for the person object to know how to update its own age. Let's grab our class from before, right here. I'll pop it into 10-3 right here. And we'll add 2 methods. 1, introduce, and 2, birthday. Introduce will print a sentence using the object's attributes, while birthday will update the object's age by 1. The idea here is when you call p1.introduce, Python will automatically pass p1 into the method as self. So inside introduce, self refers to p1. In order to define a method, we use def. Make sure that this def is indented within object person. And we'll call our method here, introduce, and we'll pass in a parameter of self. Now this method will have access to all the attributes within its own person object. So we'll have a print statement in here that will use our name and age attributes. Hi, my name is, and then we'll have self.name. And I am some age, self.age. And we've successfully here, we've defined a method for this class. And let's define another method called birthday. Also takes in itself. And we'll set self.age is equal to whatever age plus 1. And we'll pop down here and we'll initialize our object. So person is Calvin. And now we can call our methods on the object. So let's call our introduce method like that using dot notation, p1.introduce. Print that. And now you can see that it'll take the attributes that we defined here and print them in this statement. We're going to do the same thing with p1.birthday. And then let's introduce ourselves again. Because our birthday method here will not print anything, but we know it's going to run in the back. So if we just had this, we'll still only get this print line. But if we call print p1.introduce again, we should expect to see, hi, my name is Calvin, and I am 31 now. And that's what we get. The key idea here is objects can hold data and provide the functions that act on that data. The code stays organized because you don't just have random helper functions everywhere for behavior for a person. The person class will own that specific behavior. Let's work on an actual real-world example. Or let's jump into our next exercise. Create a file called 10-py, and we'll pull our class definition into the new file right here. In this exercise, I'd like to jump into a harder example. We'll create a list with 3 objects. 3 person objects, and we'll give them different attributes. So we'll keep one of me, person, John, 60, and person, Ava, 25. And now I want to iterate through this list and introduce everybody. So this would be pretty easy if we did a for loop for person in people. And we can loop through, grab each object, and call the introduce method on each one of them. So if we run this, we'll see 3 different print statements, all calling their own version of introduce, using their own attributes. So if we call this, we'll get 3 similar statements, but we'll have different attributes in each corresponding to each person object. Now, what if we wanted to update everyone's age? Same thing. For person and people, we simply just call the birthday method. And then we'll just have everyone introduce themselves again. And now here, we'll expect to see, hi, my name is Calvin, and I'm 31, 61, and 26. We've designed our methods so that we can update our object's end state. There's a lot more things I'd like to cover in object-oriented programming, and like functions, this is fundamental for your learning, so I'm going to split this episode up into 2 parts. Here, we'll save our progress using our same Git workflow, git add, sometimes the terminal is wonky, git add, lesson 10, git commit, and we'll have our message be git lecture 10, object-oriented programming part 1, and we'll push this, and we'll have saved our progress. From this video, you should be clear on what objects are. because you've already used them through methods like strip and append. You should understand that a class is simply a blueprint, and an instance is the object that is created from that blueprint. You should understand that attributes are simply data that's stored on that object. You should understand that methods are functions on the class that operate on the object, and that self is how the method refers to the current instance. You should also understand what init does and why it exists. Remember, it sets up the object so every instance can start in a consistent state. In the next object-oriented programming video, we'll build on this by covering more class features than you'll see in real life. Thanks for watching, and I'll see you guys soon. Hey everybody, my name is Kelvin, and welcome back to episode 11 of my Learn Python series. Today, we'll be going over part 2 of object-oriented programming. If you recall from part 1, we introduced objects, classes, instances, attributes, instant methods, things like that. This episode will build on that by showing you how classes behave once you start using them in larger scripts. Things like shared state versus per object state, or how to make objects print cleanly, different kinds of methods you'll see in real code. This episode will build on that and teach you a few more techniques that are crucial to object-oriented programming. If you haven't seen part 1, I strongly recommend it because the concepts in this video will build on what we already covered last time. Also, real quick before we jump in, if you've been enjoying the content on this channel and want to support what I'm building here, check out my book Modern Data, From Ingestion to Production. It's a practical introduction to how data moves through modern systems, from ingestion and transformation all the way to production use. It's available on Amazon, Barnes & Nobles, and Apple Books, and the ebook is only $6, so it's a really affordable way to support the channel and learn something useful at the same time. Be sure to check out the links in the description. Without further ado, let's jump right in. We'll create the folder for our lesson 11 here, lesson 11. And we'll create our first exercise like we usually do, 11-1.py. And in this exercise, I want to cover the difference between instant variables and class variables. In part 1, we used instance variables. If you recall, instant variables are attributes that are stored on a specific object. If you have two person objects, then each person has its own name and their own age. Changing p1.age would not change an object p2's age. Class variables are attributes that are stored on the class itself. Every instance can read them. They're used for things like shared defaults, constants, configuration values, and counters. Let's define a class. We have a class called person, and here we will have two class variables. Again, class variables are shared by all instances. So we have a person class, and we have class variable that we'll call species. And since we're a person, our species, hopefully, is human. And then we'll have count created is equal to 0, because as of right now, we've created no classes of person. We'll define our init constructor like we covered last episode. And in our init, we'll pass in name and age. And here, we'll have an instance variable called name, which is equal to the name parameter that we pass in, and self.age, which is an instance variable that we created to track a person's age. And then now, what if we wanted to update the class level state? What if upon creation of a person class, we wanted to increment count created by 1? We can do that like this. We can do person, which will reference the person class, person.count created plus equals 1. And this, every time a class person is created, will increment count created by 1. And this is shared across all created objects. Let's see it in action. So we'll have a p1 is equal to person, and we'll have it be me, Calvin, and he's, I don't know, 27. And we'll have a P2, which is equal to a person called Madison, and she'll be 24. And now we'll print P1, P1's name, and P1's age. Do the same thing for P2. And we'll also see the species. And species of myself. Oops. And P2.species. And finally, let's print person.count created. And here, since we've created two objects here, P1 and P2, both being of person classes, we should expect to see that this number right here is 2. Because every time we create a class person, this init constructor runs, and it sets the name and the age, and it also increments the count created in class person by 1. And remember, this is shared by all classes. We'll run this, and we'll see Calvin 27, Madison 24, 3 humans, which are all of these. Person.species is human, P1 species is therefore human, and P2's species is human, and then count created is 2. And that's what we get. One thing to keep an eye out for is what happens when you assign a class variable through an instance. When you write something like P1.species is equal to alien, Python creates a new instance attribute named species on P1. It doesn't change the class variable. After that, P1 reads its own instance attribute, while other instances still read the class variable. What do I mean here? Let's jump back up here. And we'll set P1 species is equal to alien. We don't need this right now. Since we set P1.species is equal to alien, now this is an instance attribute. And we should see alien. But the person.species would not change. We'll still expect to see a human, because P1.species did not update the class variable. Same thing with P2.species, because it still relies on the class variable. So here, we should see human, alien, and then human. Run this, and that's what we get. Now if we set person.species is equal to robot, notice I'm setting the class variable now. We can do P1.species, print P2.species, and then finally we'll print person.species. And now, what should we expect to see? We'll see alien, because P1.species is still alien. Now P2 species is going to be a robot, because now we've set person.species, or the class variable, to robot. And since P2.species references that variable, we should expect to see robot, and of course this will give us robot. And let's run it and see if our hypothesis is correct. And it is. Remember one thing. Use self.x for per object data. Use className.x for shared data that should be consistent across objects. And that's the key principle here. Let's move on to the next exercise. Create a folder called 11-2.py. And here I want to cover a couple more methods that will come in handy when you're working with classes. That being str and repr for clean printing. When you print a custom object without any special methods, Python will print a default object representation that is not useful for understanding what the object contains. In real projects, clean printing matters because you will print objects during debugging, logging, or testing. Python will give us two methods to control this, that being str and repr. Str controls what you see when you call print some object. This is usually a readable summary, while repr controls what you see in debugging contexts, such as printing a list of objects or inspecting objects in a console, and is typically a bit more explicit. Let's pull the person class that we created last time, and we'll use it for this exercise. Since we're not covering class attributes, since we're not covering class variables, we don't need that. We'll have our init, and then we'll create the two objects that we created last time. And now, what if we wanted to print P1 as is? Oops, we need to get rid of this because we no longer have our class attribute. Run this. And this is what we would usually get. This doesn't make a lot of sense to us. What is this? At some address memory, that's not useful for our context. That's what str and repr are supposed to be, or are supposed to be used for. We can define it like this, in a very similar fashion as the init constructor. Str, and that'll take itself, colon, and then we can return some human readable version of this object. We're going to define it like this. Dot name, squiggly bracket, self.age, squiggly bracket. And this is going to be just going to be a string representation of our object here. All we're doing here is doing something like Kelvin, in parentheses, some age. So here, for the string representation of this, is going to be Kelvin, space, parentheses, 27, parentheses. And all that's doing is just formatting your variables in case you want to print this object. Now, let's see what happens when we print Kelvin 27. And that's what the purpose of str is for. Let's create a repr method. And we can define it like underscore underscore, repr underscore underscore. And again, it'll just take itself. And we can return person. Name is equal to self.name. And age is equal to self.age. And this will be our developer or debug version. And what we created here, this exclamation mark and this R, we'll use repr formatting for the string, which is useful in debugging. So now we already have our P2, and we'll just print P1 and P2. And now down here, we can do people is equal to P1, P2, and we can print people. And what happens down here is now we use repr for each element within people. So let's print this. And now down here, you can see that we use the string method for Kelvin and Madison, but down here, we've used the repr method down here. So you can see that there's a different format here. And all this is doing is just giving us a human readable way of seeing our object. A reason why you might use repr style formatting is that it makes special characters visible. For example, what if we had a string s called Kelvin, and then we had a complete new line that we can do like that, and my last name, and then what if we wanted to just print s? This prints with a new line, but what if we wanted to have repr style formatting, and we can pass in s to our repr function, and now we'll see Kelvin /n Lin, even though it's the same string. And what this can help us with is debugging, because what if you didn't know why? What if you didn't know why there was a new line here, and we didn't know what s looked like? Using repr here would tell us, oh, we have a new line here because there's a /n. This can really help when objects appear only inside lists or dictionaries. Let's move on to the next exercise. Create an exercise folder called 11-3.py, and here I want to cover instance methods, class methods, and static methods. If you remember from part 1, we used instance methods. Instance methods operate on only a specific object, so they take self as the first parameter. They can read and modify instance variables. Class methods operate on the class level. They take CLS as the first parameter and are called on the class. They are often used to provide alternate ways to create objects. Static methods are functions that are placed inside the class for organization. They do not receive self or CLS. They are used when the logic relates the class conceptually, but does not depend on the instance state. Again, let's borrow a person class from up here. We'll jump down here, copy and paste it. But now, let's define an instance method. This is something that we've seen before, and we have birthday. Here, we also want to define another class variable called species. Is equal to human. And this instance method here will take in self, and we'll increment self.age by 1. This instance method only works on one single instance. Now, what if we wanted to define a class level method? We can do that using this notation at class method, and we can have our class method be from birth, year, and what it'll do instead of taking in self is the string CLS, or is the variable CLS, and we can pass in name, birth, year, and the current year. And here we can have age is equal to current year is, and minus the birth year. And then we're going to return CLS, name, and age. And I'll just create the static method before we move on to any more explanations. And we can do it by @static method. And we'll call this def is adult, which takes in an age parameter, and we'll return whether or not age is greater than or equal to 18. And then we'll also have some prints down here, have a person object that has me, and let's say my age is 27 again, p.birthday, print p.age, 2 is equal to person dot, and we'll call our class method here from birth year, and we'll have Madison, and say 2005 is her birth year, and 2026 is when it's now, and then print p2.name and p2.age. And we'll have our static method here, 17. I'll explain all of this very shortly. Let's jump back up here. Here, we're creating a person object called Kelvin, and it has a name, Kelvin, age 27. And what p.birthday here is that Python will call the function with the instance automatically. So within birthday, self is p. When you call person from birth year, Python calls the function with the class automatically. So within that method, CLS is person. Using CLS instead of person keeps the method correct even if you later subclass person. Static methods are basically just like normal functions. Python does not inject any extra first argument, and that's the difference here. Right here is our instance method. This operates on the specific instance. Here is at the class level, and here is static, and this doesn't inject anything before we call the function. Let's run this. And we'll say p1.birthday. We'll get 28 because now we've run that method on the p object. And then p2 right here, we have the from birth year class method, and then person is .adult, it doesn't matter what else we have in our classes and whatnot. All it's going to do is just run a simple check to see whether or not 17 is greater than or equal to 18, which it isn't, and 21, which is. So that explains the false and true down here. And that's the difference between all three. Let's move on to the next exercise. We'll create 11-4.py, and here I want to cover composition. Composition is when one object stores other objects as part of its state. This is a common way to model real programs. A course can store students. An order store line items. A playlist stores songs. Let's create two classes. Class student will represent one student, and course stores a list of student objects. The course methods will manage that list. The main idea here is that the course object owns the behavior for managing its students. Adding, listing, and searching are course responsibilities. So we'll define our classes, class student, and we'll give it a constructor, init, pass itself, and name of the student, and self.name is equal to name. And then we'll have a repr self, and we'll just return f student name is equal to self.name exclamation point r right there. And we'll have a class called course. And we'll also create a constructor here, def init, self title. And in here, we'll have self.title is equal to title. And self.students is equal to just an empty list for right now. And it'll store a list of student objects. And here, we'll have add student, which takes itself and a student instance. Notice how we're passing in the instance here. And here, we can do self.students, and we can append to our list an instance of student. And here, we'll define a method called roster, and what we'll do here is return a list of student names for display. So we'll have names is equal to an empty list here. And then for s in self.students, we're going to iterate over this list and return a list of student names. Names.append s.name. And we'll return the list of names. And here we've implemented a method to get the roster of students. And then we'll also have a find student method right here, which will take in a self and name. And what this will do right here is it's going to search. And it's going to search for that specific student. And we also want to make sure we catch all the students regardless of capitalization. So we're going to make sure it's case insensitive. So let's get target is equal to name.strip.lower. And now we have our clean name right here. And then we're going to iterate through self.student. And if s.name.lower is equal to the target name, then we return that instance. And if we find nothing, we'll just return none. Now let's jump into our actual script here. Course is equal to a course object called Python 101. And we can have add student. And again, we'll have a student object for myself. Do the same thing for Madison. And then we can print the course dot title and then print course dot roster. We can also see if we find a student. So found is course.findStudent. Oops. So we're interested in finding myself, and we know that this should return the student object right here. And we'll also have a missing with the same premise, except it's going to be for a name that doesn't exist. We know that Kevin does not exist. We know that Kelvin exists, but not Kevin. And then we can run this. Whoops. We have a typo right here. Now, we can see that we get the correct prints. Again, the main summary here is that we have students, but course will do basically all the management of the student objects here. That's the thing to remember here. A lot of code will be structured in this way. And those were the concepts that I wanted to cover in part 2 of object-oriented programming. As usual, we'll do our git workflow, git add, lecture 11. Oops, not lecture. Git add, lesson 11. Git commit, lecture 11, object-oriented programming, part 2. And we'll push this. And we'll successfully push to the course repository and save our progress. And that's it for this video. If you liked the video, be sure to like, comment, and subscribe. And be sure to check out my book, Modern Data, From Ingestion to Production. I'll see you guys in the next video, where I'll cover inheritance. Thanks for watching. Hey everybody, my name is Kelvin, and welcome back to episode 12 of my Learn Python series. In this video, we're going to be continuing on episode 11, where we covered object-oriented programming principles. Specifically, I'm going to use this episode to help you learn about inheritance. Inheritance is one of the main core ideas in object-oriented programming. It gives us a way to create a new class that is based on an existing class. That means if two classes share some common behavior or data, we do not need to rewrite everything from scratch every time. We can just define the shared parts once in a parent class, and then let the child classes build on top of that. And that's the main purpose of inheritance. Up to this point, we've been making classes on their own. Remember that a class has attributes, methods, and its own internal state. That is already useful, but very often in programming, you run into situations where multiple classes are closely related. For example, maybe you have a general animal class, then maybe you want a dog class and a cat class. A dog and a cat are not the exact same thing, but they do share some common traits. They might both have a name, or they might both have an age. They both might be able to make a sound. So instead of writing all of that common code separately in both classes, we can place the shared parts in a single parent class, and then let the child classes, quote, inherit from it. And that's the idea we're going to be focusing on. Also, real quick before we jump in, if you've been enjoying the content on this channel and want to support what I'm building here, check out my book Modern Data, From Ingestion to Production. It's a practical introduction to how data moves through modern systems, from ingestion and transformation all the way to production use. It's available on Amazon, Barnes & Nobles, and Apple Books, and the ebook is only $6, so it's a really affordable way to support the channel and learn something useful at the same time. Be sure to check out the links in the description. Let's create the exercise folder for today. Create a lesson 12 folder. In this episode, it'll be easier if we keep all of our code in a single file. So we're only going to create 12-1.py today. I'll be using the animal example to explain inheritance to you today. So to start, we're going to need a class called animal. And we can define it like this from exactly the same way that we covered from last episode, and we'll define an init. Remember, this is the constructor for the class, and it'll take in parameters self, name, and an age. And we can set self.name is equal to name, and self.age is equal to age. In an animal class, it makes sense that we have instanced attributes of names and ages. These attributes would be shared by any animal. Now, let's define a method called describe, and it's going to take in self. And what I'll do here is give us the information of name and age in a nice readable format. So print self.name is self.age years old. And that's all it's going to be doing. And let's also define a method class called speak. This will print what sound an animal makes. Since we have a generic animal right now, we'll just have it say a sound. So f self.name makes a sound. This is not speak, this is self right here. And we've defined our animal class. First, it has attributes name, age, and two methods, describe and speak. As you can see, this class is very general. We can't derive any specific animal from these because all animals can make a sound. All animals can have a name or can be however many years old. Now, let's say we want to create a dog class. A dog is trivially an animal, so it makes sense for dog to be related to the animal class. Before we create the dog class, let's test to make sure animal works. We'll create a variable, animal1 is an animal that is some generic animal, and let's say they're 5 years old. And here we have two methods, describe and speak. And let's test this. Here we get an error. Animal takes no argument. And taking a look at the code, we see that the init, I miscreated the init. You have to have two underscores on either side. And what I had before was just this. So that was why we get that error. But if we run it now, we can see that we successfully create our generic animal. Now that we got our animal class working, we want to create our dog class. Our dog class is going to inherit from our animal class. And the way we can create that is by doing class dog, and it'll inherit from the animal class. Right, like that. The class inside the parentheses here is the parent class. So animal is the parent class and dog is the child class. At the moment here, this dog class doesn't really define anything new. It just says that dog should inherit from animal. That might look too simple at first, but even with just this code, the dog class already gets access to what's defined in animal. So let's just put a pass in there for now, and we can do dog1 is equal to a dog that is named Buddy, and let's say they're 3 years old. And note that we haven't defined anything in the dog class. But it'll have access to the methods and constructor of the animal class, even if we haven't defined anything in dog. So here, we know that dog1 has the method describe, because that's what animal had, and here we have a speak. Let's run this. And we see here that it doesn't have any issues inheriting the methods. This is a very important concept of inheritance. If a child class does not have a certain method or attribute set up of its own, Python will look to the parent class. So in this case, when we created dog1, Python used the init method from animal. When we call describe, Python uses the describe method from animal. When we speak, Python uses the speak method from animal. That's already useful to us because we created a more specific class, dog, without duplicating all of the code that was already an animal. The value of inheritance becomes clearer when we imagine not just one child class, but maybe several related ones. Maybe we want a dog class, a cat class, a bird class. All of them are animals. All of them might need a name and an age. All of them might need a describe method. If we did not use inheritance, we'd end up writing the same init logic and the same shared methods in multiple places. That repetition makes code harder to maintain. Let's make dog a bit more specific. Right now, when we call speak on a dog, it says Buddy makes a sound. Sure, it's technically fine, but it's a bit too general. A dog does not just make a sound. We know that a dog can bark. So let's redefine speak, the speak method inside dog. Let's jump up here, and we'll define our own speak method here. And it'll take in self. We can even pull the code from here. Oops. And here we can change it to the dog barks. Now, dog will still inherit from animal, but now it has its own version of speak. Now we can test this again. What should we expect to see? We see that it still inherits the describe method from the animal class, but now, when we call speak, it calls its own speak method right here. And that concept is called overriding a method. Overriding means a child class replaces a method it inherited from the parent with its own specific version. That's another major reason why inheritance is useful for us. You can keep the shared parts from the parent, but we can customize the parts that should be different in each child class. For fun, let's create another class called cat. And I'll basically be the dog class right here. So just copy and paste this. And we'll have it be meows. And we can create it in basically the same way. Have our cat called Whiskers. And our cat, let's say, is 1 year old. And this will be stored in a variable called cat1. We see that it works. Now, both dog and cat inherited the same structure from animal, but each one has its own version of speak. Speak here, Prince will bark, and the cat will meow. So far, the child classes only change behavior by overriding methods, but child classes can also have extra attributes that the parent class does not have. For example, maybe every dog also has a breed. The parent animal class does not know anything about breed, and that's something more specific to dogs. So now we want the dog to keep the inherited name and age, but we will also want to add an additional breed attribute. And here, all we need to do is go up here. We'll define another constructor within class dog. And we can use basically the same structure here, but now instead, we're going to also pass in a breed parameter. And we'll just define self.breed here is equal to breed. This way will work, but it's not completely ideal. Why is that? Because we're rewriting part of the code. So name, age, we have self.name and self.age already. That's just duplicating code. What we can do is reuse the parent's init, then add only the new child-specific part, and that's where the super method comes in. So here, we can just change these two attributes right here to super, parentheses, and then dot. Get the method, and then name and age, and now here we have referenced the init from the parent class, this goes up to a parent class, and then this gets the init from the parent class. And now we can add our own attribute here. This allows a child class to extend the parent class's behavior without copying and pasting the parent's code. Now, let's test this version. Say we had Buddy, and let's say he's now a golden retriever. Now we're curious about what his attributes are. So dog1.name, dog1.age, and dog1.breed. And now we run this. Now we see that the dog class has instance attribute of Buddy, 3, and golden retriever that is exclusive to only the dog class. And we see that the methods still work. We can do the same thing for the cat class. Let's pull our method from the dog class and let's put it into the cat class. And instead, we're going to be interested in whether or not it's an indoor cat. And this will be a parameter that's either true or false, because if you're an indoor cat, then you can't be an outdoor cat. If you're an outdoor cat, then it doesn't make sense that you're also an indoor cat. And now we can get the init method from animal, and here we can set indoor is equal to the parameter indoor that we pass in. And now we can adjust our code down here to create a cat object that is indeed an indoor cat. And we can verify this as well. And we'll just print indoors to save time. We can run this, and now we get true. And that's what we expect. The cat-specific attribute is added in the child class, and that's the balance inheritance gives us. We can reuse the same structure from the parents and add or modify what is specific to the child. One useful way to think about inheritance is with an is-a relationship. So, for example, a dog is an animal. A cat is an animal. A bird is an animal. And that's why inheritance makes sense here. The child class should be a more specific version of the parent class. And that's usually a good sign that inheritance might be appropriate. If the relationship does not feel like an is-a relationship, then inheritance may not be the right tool for you. For beginner examples, this parent-child relationship is usually a good way to understand the concept. The main idea in this lesson is that inheritance lets one class build on another. A parent class will hold the shared attributes and methods, while a child class will inherit those shared parts and can also add its own attributes, define new methods, or override inherited methods. In our example, to sum it up, animal was the parent class, and we had two child classes, dog and cat. We inherited the describe method from animal. We overrode speak in the child classes, and then we referenced the animal class using super, where we reused the parent's init. And that's what I wanted to cover in today's lesson. As always, let's do our git workflow, git add, lesson 12, and git commit lesson 12. We'll push to our course repository. Thanks for watching, and I'll see you in episode 13 of my Learn Python series. Hey everybody, my name is Calvin, and welcome back to my channel. Today we're going to be covering episode 13 of my Learn Python series. In the previous episode, we covered inheritance in object-oriented programming. In this episode today, I'm going to cover a couple more concepts, called encapsulation and abstraction. These are two object-oriented programming concepts that affect how a class manages its data, and how the rest of a program will use that class. What does encapsulation mean? Encapsulation means placing an object's data and the rules for changing that data inside the same class. Some attributes can be public and changed directly without causing a problem. Other attributes need to follow rules. In those cases, the class can provide methods that control how that value changes. Abstraction means providing a clear operation without requiring the caller to manage every step inside that operation. A method can combine several smaller actions into just one useful command. Start will create our lesson 13 folder like before, and we'll create a file called 13-1.py. Here, we're going to be just using a simple bank account example for this entire lesson. Let's start out with a skeleton. We'll define a class called bank account, and we'll have our init constructor here that will take an argument self, owner, and balance. We want to define who the owner is and the starting balance. And we'll set self.owner equal to owner, set the attribute balance is equal to balance. And let's make sure that our class works. Create bank account owner self with a starting value of 500. Then we can starting balance. Count balance. Run this and we see starting balance 500. The class here stores the owner and balance as normal public attributes. We've already used public attributes throughout the previous object-oriented programming lessons. Here, the important part for this lesson is that any code with access to the account object can replace the balance directly. What we can do here now is set our account balance equal to -1000. And then we can print our updated balance, and we should see -1000, the -500, and -1000. Here, there is no method that was involved in that assignment. The bank account class has no opportunity to check the new value or reject it. Python simply replaced the original balance with our updated value, -1000. For this example here, let's assume that the account should not be allowed to have a negative balance. Public attributes are not automatically bad. A class can use public attributes when direct access is reasonable here. The problem here is that the balance has rules attached to it in this case. We can't have a negative balance. Deposits should increase the balance, and withdrawals should only succeed when enough is available. We could, theoretically, place an if statement everywhere where the balance changes, but then the account rules would be spread throughout the entire program. Every part of the program would need to remember how a valid deposit or withdrawal works. A better design, then, is to put those rules inside the bank account class. The object will store the balance, and the class provides the valid ways that we can change it. And that's going to be the encapsulation we're going to add next. The first change that we're going to do here is change how the account stores the balance. We'll change our attribute to start with an underscore. The leading underscore here is a Python naming convention. It communicates that underscore balance is intended to be managed within the class. Underscore here doesn't make the attribute completely private in this scenario. Python would still allow someone to access account._balance directly. Underscore here then in Python tells someone using the class that they should use the class's public interface instead. This is a bit unlike other languages like Java or C. Python doesn't completely block access to underscore balance. Someone could still write something like account._balance or assign a different value to it. The underscore tells someone using the class that they should avoid doing so, and use the public operations that will be provided by that class. And that's how encapsulation is commonly handled in Python. Python generally relies on clear class design and naming conventions rather than strict public and private access rules that you might find in languages like Java. Here, we're also going to be adding a check before storing the starting balance. We'll do something like if balance is less than 0, meaning it's an invalid balance, then we set balance equal to 0. This prevents the object from beginning with a negative balance. Encapsulation applies when the object is created, as well as when it's changed later. If the class accepted an invalid starting balance, the account could begin in an invalid state before any methods were ever called. After the check, the validated value is now stored in underscore balance. We'll also add a property. The add property decorator allows this method to be accessed using attribute syntax. And then here, it's just a simple get method, balance. A normal method is called using parentheses. For example, you might write something like account.deposit parentheses 200 parentheses. A property here is accessed without parentheses. We can just write account.balance. Python will still run the balance method. That method returns the internal underscore balance value. This class now has an internal name and a public name for the balance. Outside of the class, the balance is now going to be read through the balance property. Let's demonstrate that. We'll adjust our print statement from before. We have a different print statement. We still have account.balance. Now, this will call on this property right here. And we can run the file, and we can see that we get 500. And what's the point of this? Now, if we wanted to assign account.balance outside of the property, this is not going to be possible. That's the point of that. A property can have a getter and a setter. The getter here defines what happens when the value is read. For example, our property method here only returns self.balance. You can't go ahead and change the balance without using this property anymore. We can see that when we try to set account.balance is equal to 1000, we get an attribute error, and that's intentional. I don't want the account balance replaced through direct assignment. I want the class to provide specific operations that control how the balance changes. And that property gives the rest of the program a simple way to read the balance while the internal value remains managed by the class. Let's add a couple more methods into the bank account class. We'll define deposit, which will take self and amount, and it'll perform a check for us. If amount is less than or equal to 0, then we want to print an error statement, deposit amount must be greater than 0, and we should return false. And we'll update our balance if not true. And we'll also add a corresponding withdraw method. Taking the same parameters, and we'll also check the amount that we're withdrawing. Amount it's less than or equal to 0, then we statement like before. False. And if the amount is greater than self.balance, which is our withdrawal check, we print insufficient funds. False. If both of these checks pass, and then and only then can we actually withdraw the amount. We'll turn true. What did we do here? The deposit method gives the class a controlled way to add money now. The amount must be greater than 0. If the amount is 0 or negative, the method will print a message and return false. The return statement ends the method before underscore balance is changed, and that means invalid values never reach the balance update. The important design change here is that the code outside the class does not calculate a new balance and assign it. It requests a deposit. And going forward, we can increment our bank account balance by doing something like this. And here, we should be able to see that our balance is 700. The withdraw method follows a very similar structure, but it has two rules instead of one. Amount must be greater than 0, and the account must contain enough money to complete the withdrawal. Our bank account class here now contains the balance and the rules for changing the balance, and outside code does not need to repeat those rules. Now we can do count, withdraw, $100, and we'll try to draw more money than we have, then we can balance here. See our final balance after these transactions have gone through. What should we expect here? We start with a starting balance of 500, deposit 200, which gives us 700. We withdraw 500, giving us a balance of 200, and then we try to withdraw 700. That's not going to work though. We print insufficient funds. Balance of 200 and final balance of 200. And that's the main encapsulation example for the lesson. The balance is stored internally, exposed through a property, and changed through methods that enforce the account rules. Owner remains a normal public attribute because there are no special rules connected to this in this example. Encapsulation does not require our attribute to become internal, and is most useful when the class needs to protect the consistency of a particular value. The account now can process deposits and withdrawals. Now I'm going to use those methods to create one larger operation. Let's add another method called transfer_to. We'll take in self, other account, and an amount to transfer. If not, self.draw amount. If we're not able to withdraw anything, we return false. And if our checks pass, then we can deposit our amount. True. To test this, we can create two new accounts. We can create a checking account, bank account object with me, and a starting value of 500. And we'll also create a very similar one, savings account, instead we'll have this start at 200. And then instead we'll have this start at 200, print statements, transfer, our checking balance, checking balance, and we'll also check our savings account. And here we'll use our transfer_to method to transfer $200 from our checking to our savings account. To checking account, transfer to savings account, and here we'll check it again. Let's run this completed program. And here we can see that our transfer successfully completed. We've successfully decremented 200 from our checking balance and incremented our savings balance by 200. Notice that without this method, the caller would need to coordinate the two operations itself. We'd have to have something like if checking.withdraw, then savings.deposit. And that's manageable in a small program, but it places responsibility for the transfer process outside of the class. If several sections of a program perform transfers, the same sequence could be repeated in multiple places. And that's the abstraction in this example. The caller requests a transfer, and the class handles the withdrawal, the failure check, and the deposit now. Our final bank account class demonstrates both concepts. Encapsulation is shown by the internal _balance attribute. the read-only balance property, and the deposit and withdrawal methods. Abstraction here is shown by the transfer method. The caller uses one clear operation instead of multiple. The class handles the smaller steps needed to complete that operation. Encapsulation keeps an object's states and its rules together, and abstraction gives the rest of the program a simpler way to use that object. And that's the crash course in encapsulation and abstraction. It's a very important concept that you'll need for object-oriented programming. It may not be as essential for use in Python, but it'll help you immensely if you ever decide to work with languages like Java or C. As usual, let's stage our changes, which is git add less than 13. We'll write a commit message, lesson 13, encapsulation and abstraction, and then we'll push this. I'm here. Push our repository. Thanks for watching, and I'll see you guys in the next lesson.